This is a short talk on the photoelectric effect. It includes an introduction to photoelectron spectroscopy. And this is put together after a presentation by Shaina Mavrin Villarosa. The photoelectric effect has been known for well over 100 years. Heinrich Hertz in 1887 observed that electrodes, and remember that electrodes are anything that we can connect then to some sort of voltmeter or ammeter. Electrodes that are illuminated with ultraviolet light, that's beyond the violet, beyond the visible spectrum, create electric sparks more easily than those that are not illuminated with ultraviolet light. You will recall that in our model of the atom, specifically the model of the metallic atoms, that we consider the metallic nuclei to be a kind of like a bunch of islands that are set in a sea of electrons. The electrons are just waiting to be set free. The incoming radiation now we see from modern theory is knocking some of the electrons out, and that makes it easier to create sparks from these electrodes. The ultraviolet light then provides the energy necessary to make the electrons move away from the surface, break that bond with the nuclei. Photoelectric effect refers to the emission or ejection of electrons from the surface of a substance. This is generally a metal, and this ejection is a response to the incident light. In this case, ultraviolet light is used. So as you see on the diagram, the waves show the ultraviolet light coming in, and the electrons with the arrows are being ejected from it by that energy. In the photoelectric effect, electrons are emitted from matter, mostly metals, and this is a consequence of their absorbing the energy from the electromagnetic radiation. The energy must be short wavelength and high frequency. Ultraviolet light is one of those that works, but X-rays will also work. Electrons emitted in photoelectric effect investigations are referred to as photoelectrons. The photoelectric effect requires photons with energies from a few electron volts to over 1 million electron volts if you're using the high atomic number elements. The study of the photoelectric effect led to very important steps in understanding the quantum nature of light and the quantum nature of electrons, and ultimately influenced Einstein, de Broglie, and others to form the concept of wave-particle duality, the idea that tiny particles like electrons can act like waves, and very high-energy waves can act like particles. Einstein, in 1905, published a number of incredible papers, 3 papers in the same journal of the Annalen Physics alone. He interpreted the photoelectric effect and gave us equations which are valid for visible and ultraviolet light. He said that the energy of the photon, the incoming photon, is equal to the energy needed to remove an electron plus the resulting kinetic energy, energy of motion of the emitted electron. And he gave us the equation h nu, Planck's constant, times the frequency, equals W plus E. Now, W is a work function. That's the minimum energy required to remove the electron from the surface. That's the energy needed to pull the electron away. E then is the maximum kinetic energy of the ejected electrons. And it's equal to 1/2 times the mass times the square of the velocity. Of course, mass is the rest mass of the electron. V is the velocity or speed of the ejected electron. The bottom line is this. If the incident photon, the photon that hits the metal, has an energy less than the work function, and remember that's the energy needed to tear the electron away from the atom, then no electron will come off. That was Einstein's, revolutionary notion that a certain package of energy is needed, and if that package of energy is too small, no electrons will come off at all. Before, we had thought that the more photons that came in, the more light that came in, the more electrons would be ejected. But there is a threshold energy, or that won't happen at all. In his model, the photon is localized. It gives all its energy, h times frequency, to a single electron. I say one photon, one electron. And according to Einstein, the maximum kinetic energy for the liberated photons is given by this equation. The work function, which is shown here as the Greek letter phi, that looks like a 0 with a line through it, in electron volts, is going to be depending on what the metals or other substances are. And you see this from sodium, aluminum, copper, and so forth. And this tells us the amount of energy needed to strip off one electron from this type of atom. The question is, does this make sense? If we think about it, it certainly does. Notice the work function for sodium, 2.46, and for iron, 4.50. Iron is considerably greater than sodium. From your understanding of the electron configurations, is this a reasonable result? Is this a reasonable set of numbers? Well, yes, it is. And here is a problem that will help us see that. Electrons are emitted from a metal when a light with lambda, wavelength of 272 nanometers, strikes it. But higher wavelengths cause no electron emission. What's the frequency? Well, we use the speed of light in our formula, which tells us that the speed of light equals wavelength times the frequency. And then we can figure the minimum energy in joules needed to eject electrons from this metal. We are given Planck's constant here. Now, this leads us to photoelectron emission spectroscopy. Photoelectron emission spectroscopy is a relatively new concept in the AP curriculum. And you can see here a photon source is aiming high energy light, typically either UV or X-rays, at a sample at a given angle. There are two angles here because this is a three-dimensional picture. The electrons are emitted and sent into an energy analyzer, which is kind of like a mass spectrometer. And the energy then can be plotted against the number of electrons, the signal that comes off. This is done, of course, in a very, very high vacuum. Now, here are signals that result from using hydrogen and helium. And let's look carefully at these. The relative number of electrons is plotted on the vertical axis for each of these. And let's look at hydrogen. You'll see that it has a peak of 1 at an energy of 1.31 electron volts. Compare that with the helium, and you'll notice that nothing happens until 2.37 electron volts on the energy. And when that happens, the peak is twice as high as that of hydrogen. Now, if you look at your periodic table, you can see that hydrogen has how many electrons? Well, it has 1 electron. Helium has 2 electrons. Does it make sense to you that the helium would need more energy to eject electrons, and that you get twice as much out of the helium as out of the hydrogen? Certainly. Which element needs more energy to knock out an electron? Well, in helium, you've got 2 protons pulling on 2 electrons, and that's a force that's, roughly twice that of the force pulling on the electron of hydrogen. And as you can see, the energy involved here is almost twice the energy needed with hydrogen. Again, which element loses more than 1 electron for the same energy input? Again, it's helium. Helium loses both electrons that it has, but it needs a much higher energy in order to do it. This ends our talk about the introduction to the photoelectric effect and photoelectron spectroscopy. We will go more into that when we look specifically at the various PES plots for several elements.